You know, it's Darwin Day, and you know what that means? A storm. I've looked back over the records here for the last 614 years that we've had Darwin Day here in Sacramento, and I remember some of you at the very first one, around the time that Queen Isabella and King Ferdinand were given that bid by that guy named Columbus. And it seems to have rained every single one. It's really funny, because I checked the records to make sure I wasn't imagining this. January, there was not any rain whatsoever. None. At all. It's like we got it all in December and February, so I fear for April. Folks, this is a Darwin Day event as always, and I want to, before I go any further, introduce one of the main forces behind Darwin Day, and of course, that is Minga Futrell. That's all right. Well, I'm looking on the program, and I'd like to have everyone who's involved in the event, first off, be thanked for it. But I'm apparently supposed to introduce Minga according to the program at some point. So, if everyone involved with the planning of Darwin Day would please stand up. That would be Bronda, that would be Ken, that would be all the other names involved with it. Please, give yourselves a bow. We're all humble today. And as always, we are a crack outfit here, getting organized on time. So, a couple things I want you to be aware of course, as well. We are past the 200th anniversary of Darwin's birthday, which was in 2009, which means it's the 206th birthday for Charles Darwin. And it has been brought to my attention that part of the event here, we do actually sing Happy Birthday to Charles Darwin. I'm told that, and we will hopefully be carrying on that tradition if I do not have laryngitis by that time. So, we have some live music coming up. We have a couple of things as well. What I would like to do at the moment, if you're ready, is have Minga come up and say a few marks about Darwin Day in general, if you'd be so kind. Thank you, Minga.
Well, welcome to all of you, and thank you for ignoring weather reports or whatever and coming out. I look like a drowned rat. When I was loading some of the stuff to bring, it accidentally went into the gutter downtown in the middle of the rain. So, sorry. Don't look at me. Just listen. Anyway, I'm extending this welcome to all of you on behalf of those of us on the Volunteer Organizing Committee, and you will see our names listed on your program. But I'll say about us that we are simply science enthusiasts, and we want to toast science for its benefit to all of humanity. There are local celebrations in other parts of the nation, and each one is marking in some way the birth of Charles Darwin and his accomplishments and his superb contributions to human understanding. And there are events around the world too. They are got all kinds of variety: lectures, sermons, museum exhibits, films, showings, parties. We're kind of a party. All are annually commemorating Darwin Day to remind us of the benefits of science and how different our world is now because of what he did way back then. This coming Thursday, as Liam said, is the 206th birth anniversary, and it was someone who made quite a splash in his day, although not necessarily a popular splash at the time, and even now not very popular with some people. Darwin's Shake-Up was the revolutionary publication of his The Origin of Species, and his daring idea has gone on to produce a far more permeating effect on our lives today in many fields of science and all across the world. Contemporary scientists deem his theory of evolution through natural selection as the most powerful scientific theory ever developed, and in many ways it just keeps getting stronger and better as you might say it too evolves. Today, let's celebrate not only Darwin, who he was and remains a scientific giant, and his contribution to the progress in many areas of science that has taken off since he and Alfred Wallace first put forth the proposition about the mechanism by which evolutionary change takes place. but also science itself. According to some college-level science departments, we have, I think the name of them over there, they endorse Sacramento's event. Sac State's Biological Sciences and Anthropology departments have, and Sacramento City College's Physics, Astronomy, Geology, and what, Liam? Biology also have endorsed our event. And then we have some nonprofit groups that provide either in-kind or financial support as well. At our event, we welcome science enthusiasts of every stripe, religious or non-religious, and particularly educators, because we want to promote and defend science education in curricula and public school programs. And do we ever need it? With, seriously, anti-intellectualism growing to new heights in this nation, and with climate change apparently gaining in speed while so many of our lawmakers are still denying the science of it, citizenry like you with a grasp of science can be the strongest defense, we hope, against the unsettling future that we face. So along those lines, you should be aware that this year is a renewed emphasis on the idea of promoting February 12th, Darwin's birthday, that's coming up, as a day for annually celebrating science and certain human values across the world. There's a newly revamped International Darwin Day Foundation website that points to the special characteristics of Darwin himself that could be celebrated and promoted globally within humankind. Perpetual curiosity, hunger for truth, intellectual bravery. Well, perhaps he did finally come around on that one. However, we or they at that foundation might choose to express the values of science. That international effort is urging us this year that we all work locally to create officially recognized holiday that will inspire people across the world to reflect on and act on those values, however we define the values of science. And at our own local event today, we want to encourage you, any of you, who would like to join with us and take steps during the year 2015 to urge local and statewide politicians to acknowledge this global event, Darwin Day, annually. You can join our organizing committee and help us to champion evolution and science, not only by ways of growing our local celebration here, but also getting influential folks in the political arena on board. If this interests you at all, we would love to have your help out this year. So please see me after today's program with your interests. We'd love to have you join. It's important to recognize, and we do, the great diversity of folks who appreciate how important evolutionary theory has been to human understanding of the natural world. Darwin has become a symbol of scientific advancement that can and should be promoting a common bond among all of Earth's people and not divisions over ideology, especially between religious and secularism that continues to impede educational progress. So in the current social and political context, we've got to work harder. We have got to work harder than ever to preserve sound science as a hope for humanity. And we need allies in our desire to succeed in that preservation. So I'm going to name a few names because I think I've had so much help on the organizing committee. The new co-chair of this event, high school biology teacher Deborah Smith, along with Ruth Rizos, Bill Potts, Ken Nahigian, those folks. We've had insistence in putting on the event from other science enthusiasts who volunteered for key roles, such as refreshments. And of course, I don't want to forget the co-sponsors and outreach tablers. We're grateful to all of them. So let's applaud them all. delighted that some of the organizations that have pitched in this year have been able to make it through the rain here, and they have representatives. So I want to mention their names because I want you to really support these organizations. They're nonprofits. The National Center for Science Education over here with Glenn. We have Camp Quest back there with Liz. Maybe hold your applause and let me run through them. We have the Humanist Association of the Greater Sacramento Area. Wendy and Tom are over there. Would you stand up when I mention your name, folks? The Mountain Lion Foundation is a supporter. It looks like they didn't make it today. The Atheists and Other Free Thinkers, Ken is back there. The Brand New Reason Center, Rachel. And Americans United for Separation of Church and State, Carol. So now, thank them all. If you haven't had a chance to visit those tables, please do that after the presentation. We organizers call our event a gala, an educational gala, so we can turn on your minds to science, and then we have a social afterwards. So we want you to have some fun. Make sure you see the cartoons along the side and have some refreshments. Here's how we celebrate Darwin. We eat up his birthday cake. But of course, the most important thing is the music and the speaker, so have a great day.
Thank you, Minga. My original remarks were pretty prefatory, and I apologize because given in how many countries I can never return to, I assume everybody knows who I am. I'm William McDade at Sacramento City College. I'm the astronomy coordinator, and I have been teaching critical thinking and astronomy for over 20 years, so I think I pretty much decided a long time ago which camp I'm in, as it were. We have a great program coming up for you today as well, and pretty much as far as what Minga said, yeah, what she said. I can't really add to that, so I'll just leave it at that. I do want to point out one thing, though. Ken actually has the table back there, but Ken at the moment is actually right up here, so you might want to say hi to him as well at some point. We have Jeffrey Hale from Scientific Jam, who's going to be performing for us right now. I want to introduce him. And I am sure he's going to regale us with many, many, many songs about science before we get started in a bit. So again, Mr. Hale, thank you.
How's everybody doing? Yeah, I'm glad to be here this year. I was supposed to be here last year, but didn't make it, so I made it this year. So thank you, Minga, for inviting me. My name is Jeffrey Hale. I'm the founder of the Scientific Jam. I picked out a few songs here to start this party. So let's get this party started. The first song I'm going to sing about has gotten some people in trouble. It's about an idea that's gotten some people in trouble. This one, a pretty basic idea, landed Galileo in jail. I call it 8 planets. This is the story of 8 little planets way out there in the Milky Way. We got sun and Halley's Comet. We got night and day. The sun's a sinner, it's a star. It's closer to us than the other stars are. A hot ball of gas and a burning flame, right in the focus of elliptical plane. 8 planets circle the sun. The sun's a center of a solar system. Round they go in revolution. It's our solar system. A planet's a body of rock and gas, orbits the sun in the elliptical path. 8 planets evolve our sun. Can you name each Then comes Venus and Earth and Mars. The inner planets are rocky hard. I said, 8 planets circle the sun. The sun's in the center of our solar system. Round they go in revolution. It's our solar system. The outer planet is not so hot. Jupiter has a great red spot. Saturn has a system of rings. Neptune is the blue king. What's the planet with the greatest season? Must be Uranus for a very good reason. It rolls on its side as it orbits the sun. In Earth years it lasts 21. Circle the sun. The sun's in the center of our solar system. Round they go in revolution. It's our solar system. Used to be a planet, now it's only a rock. It has a twin. Is it a moon or not? Well, I don't care what they say. I love Pluto anyway. 8 planets circle the sun. The sun's in the center of our solar system. Round they go in a revolution. Thank you very much. Thank you so much. Great to be here. My name is Jeffrey Hale of the Scientific Jam. This next song I chose is about a conversation that started about 2,000 years ago. It was a conversation between Democritus and Aristotle, and it's only taken us 2,000 years to finally figure it out. Can you fathom the atom? Let me tell you about a small thing, baby. It's so small and I don't mean maybe. It's so tiny that you can't even see. It's so tiny that it's hard to believe. Can you fathom the atom with its particles of 3, with the protons and the neutrons in the nucleus and electrons in the outer ring? Elements have their own little atoms that give the element its properties like size and shape and atomic weight. Oxygen is number 8. Can you fathom the atom with its particles of 3, with the protons and the neutrons in the nucleus and electrons in the outer ring? Now atoms come together at least by 2. They start to form molecule. A molecule can be a compound when different atoms can be found. Can you fathom the atom with its particles of 3, protons, neutrons, electrons, and a few more little tiny ones? This next song is about one of Darwin's favorite things, I think. In fact, he used the topic is part of his support for his theory of evolution. Whether you're a giant sloth or a frog or a human, we all have these genetic manifestations. Boom. The cranium and mandible are bones of the skull. They sit on top of your backbone. The clavicle's the collarbone, the scapula's the blade of our shoulder. Now that's how we're made. Bones of the spine, vertebrae and disc, a tail at the end, saccharin and coccyx. Attached to the hip bone, the pelvis, the number of bones is 206. The skeleton from head to toe, it holds you up, it makes the blood that flows. Bones protect what's inside, and yes, those bones are alive. Metacarpals, carpals, hands and wrists. Phalanges are the fingers now, grip and make a fist. Radius and ulna and humerus are bones of the arms now, reach and blow a kiss. Our thigh bone is the longest bone, that's for sure. It's a real long bone called the femur. Tibia, fibula, patella are bones of the legs. Let's all stand up. Here's the skeleton from head to toe. It holds you up, it makes the blood that flows. Bones protect now what's inside, and yes, those bones are alive. Yeah, they're alive. Now, bones of the hands are much like feet. Metatarsals, tarsals, and phalanges. Calcaneus bone is in your heel. Now you know your bone. How does that feel? The skeleton from head to toe, it holds you up, it makes the blood that flows. Bones protect what's inside, and yes, those bones are alive. Here's the skeleton from head to toe, they hold you up and make the blood that flows. Bones protect now what's inside, and yes, those bones are alive. Thank you, Minga, for having me out. This is it's going to be a fun event. All right, so a couple more songs here, and I'll be turning it over to our speaker. I thought it would be appropriate here now to sing a song about science, because probably we're all here because we have some kind of passion for science. So this is the first scientific jam song I ever wrote. Kind of got it all started. It was the first song I wrote for the Scientific Jam, and it's called The Scientific Jam. Ask a question, find out what the answer is, guess at the answer. Form a hypothesis. The scientific method can make you very smart. If you want to solve a problem, that's a good place to start. Is your hypothesis wrong? Is your hypothesis right? If your experiment goes as planned, then you answered your question with the scientific jam. data, now you're searching for a clue. You just might want to graph it so you'll have a picture too. With careful observations, you really thought it through. The answer finally hits you and you're ready to conclude. Is your hypothesis wrong or right? Do a test that can shed some light. If your experiment goes as planned, then you've answered your question with the scientific jam. Now just in case you've made a major breakthrough, do the test again just to make sure it's cool. Some other science dudes may wanna do your gig. A repeatable experiment is something they can dig. Is your hypothesis wrong? Is your hypothesis right? Think it through, analyze, then conclude with a great surprise. Thank you for having me. So, yes. I do, yes. I actually am a middle school science teacher. I teach at Livermore Christensen Middle School in Livermore, California, and been doing it for 24 years now. Have a few more to go. So, we're good, or we want one more song? Do we have time? I don't want to take time. We got time for one? All right, okay. Just a 2-verse one now. Well, I think we have a lot of astronomers here tonight, right? So I hope I got it all right. But, What's the sun? What's it like? Why is the sun shining oh so bright? Sending energy out in waves, ultraviolet, gamma, and tiny X-rays, micro radio waves of vision. These are electromagnetic spectrum. Here comes the sun, here comes the light. Here comes the sun, shining brightly out. Here comes the sun with all its might. Here comes the sun into life. The sun's a star of hydrogen gas. It fuels the present, it fuels the past. For a great long time the fuel will last. In the fusion of helium gas, and in the core the fusion's going on, sending energy through the radiation zone, through convection zone and the chromosphere. The corona is the atmosphere. Here comes the sun, here comes the light. sun into life, 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 life. Thank you very much. I'm Jeffrey Hill of the Scientific Jam, scientificjam.com, and there's a lot more science songs there. You can listen to them for free.
Jeffrey Hale, ladies and gentlemen. Are there CDs on sale?
I do not have CDs, but if you would like a MP3 file, just email me, jhale@scientificjam.com. It's on the website, and I will send you directly to you a MP3. Okay, and I'll for this event, it's free. So you can have an MP3 file. If you email me, I'll send you, choose a song or two or few, and I'll send you that. Thank you.
Thank you very much. Okay, folks, let's get started with the main event. And we have been lucky enough from time to time to have speakers of great eminence to come to speak to us on Darwin Day. Today is one of those days. And I am happy to say he is in my discipline, which so far that hasn't happened, so that's kind of nice. Dr. Mario Livio is a senior astrophysicist at the Space Telescope Science Institute, which is the institute that actually runs the program of the Hubble Space Telescope, the legendary telescope of fame and fortune. He has published more than 400 scientific papers and 5 popular science books. His book, The Golden Ratio, has won him the International Pythagoras Prize. And if you're familiar with the golden section, the golden ratio. His most recent book, Brilliant Blunders, was a New York Times bestseller and was selected by the Washington Post as one of the best books of the year. Now, with all those honors and many, many more I could spend half an hour talking about, you would think that would be enough. But I'm going to take a guess out here that any of you that are under the age of 40 have seen him on The Daily Show. Am I right? Let's see some hands. Yeah, that's what I thought. Okay, without too much further ado, I also want to emphasize one more thing before we start as well. His book is not here, unfortunately. However, please avail yourselves of buying it at an opportunity at Amazon or some other fine bookstore among you. All right, without any further ado, Dr. Livio.
Darwin Day, that's a very nice occasion. It's a very nice event that you're organizing here. I've been writing this book, Brilliant Blunders, and while I was writing it, people kept asking me, what is your book about? And I used to say, it's about blunders, and it's not an autobiography. And now, actually yesterday, Deborah asked me also, why did I decide to write a book about blunders? And there are several reasons, but let me just say one now, and then I'll talk more about this at the end. Basically, first of all, it's comforting to the rest of us to know that even the biggest luminaries have made some serious blunders. But also, I wanted to correct a notion that science is some sort of a direct march to the truth, which is, nothing can be farther from the truth. So I will get back to this as I go along. The book is about 5 scientists, but I'm going to talk here only about 3 of them. The 5 scientists that I've chosen are actually all connected through one thing, and that is the thread of evolution. And by that I mean evolution of life on Earth, evolution of the Earth itself, evolution of stars, and evolution of the universe as a whole. So the thread of evolution runs through my 5 scientists. The 5 scientists are Charles Darwin, Lord Kelvin, Linus Pauling, Fred Hoyle, and Albert Einstein. Now here I'm going to talk, as I said, just about 3 of them. There was another reason why I chose this particular 5, other than the fact that they are connected by this thread of evolution, and that is I didn't want to go too far back. You see, if you go very far back, like to Aristotle, well, nothing Aristotle said about physics was right. So it's even hard to choose which blunder to talk about. Now, this does not make him any less of a genius than he actually was. He just worked in a very different time. So I decided to go only way to the middle of the 19th century, basically, when I talk about this blunder. So let's start. The first thing you notice about life on Earth is how diverse it is. It's enough to go out here, you know, and you will see so many plants, you will see birds, you will see insects, you may see people walking their dogs and so on. Nobody actually even knows precisely how many species there are on Earth. The latest very serious attempt to put a number on that put it at 8.7 million, but actually estimates range all the way from about 5 million to 100 million. And the reason this is such a wide range is that, you know, you take 1 teaspoon of dirt from under your feet, there are already thousands and thousands of species in that. As you know, they discover new species every year. So, you know, there are in the millions. The second thing that is very typical of life on Earth is an enormous degree of adaptation and also symbiosis, which is this sort of scratch my back and I'll scratch yours type relationship. You know, the bee has exactly the size that it fits into the flowers on which it feeds, and then the bee goes to other flowers and the pollen gets on its body and it transfers. You know, everything looks extremely well adapted. Now, it was these two things and this high degree of adaptation. You know, here I just put a picture of this clownfish that, you know, it lives among the poisonous tentacles of the sea anemone, and, you know, the fish protects the anemone protects the fish has on its body this special mucus that protects it against the poison of its host, and so on. Now, this degree of adaptation and so on is what has convinced naturalists many centuries, throughout many centuries, that there must be some guiding hand and some design and blah and blah, until something happened. And the something that happened was this gentleman. Here he is late in his life. And this was the first copy of his book on the origin of species by means of natural selection, which appeared in 1859. Now, one of the things I actually like to do when I write books is I actually go to the places where the people that I discuss worked and so on. So in this particular case, I actually held in my book in my hand the first copy of Darwin's book and so on, and in fact many of his papers and so on. So this is a very, very interesting feeling. By the way, I was asked to say something about curiosity as well, because somebody found online my TED talk on curiosity. And I'm not going to give 2 talks, because then that will keep you from the food and everything. But as you can imagine, Darwin was this incredibly curious person. I mean, in fact, in 1828, when he first arrived to Cambridge, he became an avid collector of beetles. And there is one story that he went once and he removed some bark from a tree, and there were these 2 ground beetles, and he caught one in each hand. And just as he was holding those 2 beetles, he saw actually a much rarer crucifix beetle there. But he didn't know how to catch it, so he put one of the ground beetles in his mouth so that he would be able to catch the crucifix beetle. Now, that particular story didn't end so well, because the beetle in his mouth actually released some chemical, some disturbing chemical, and he had to spit it out and actually ended up losing all 3 beetles. But it just shows you how curious he was. You know, he really wasn't going to give up even that 1 beetle. Now, this figure here, I've put it not because it is correct, because it isn't. but only because I liked it from a graphics design perspective. It supposedly describes evolution. The reason I say it's incorrect is that it sort of gives you the impression that things here are somehow more evolved than things here. And that's not how evolution works. Evolution is not a ladder. It is more like a bush. Namely, things evolve in different directions. But things that are equidistant from the starting point, they are equally evolved. So it's not that those are more evolved, but still, from a graphics design, it's gorgeous. There is one thing which Darwin didn't like to do, and that was he actually never published a genealogy tree. But he did draw them in his notebooks, and I held this particular one also in my hand to help his thinking. But he never published them, but he did hold it. And I like this one very much because, you see, this one has primates down here and it has men up there. So I like this particular drawing. Okay, what was this theory of evolution that Darwin came up with? So that theory was based on was standing on 4 pillars, and those pillars were evolution, gradualism, common descent, and speciation. And those 4 pillars were supported by one grand mechanism. Now, that figure there has nothing to do with Darwin's theory of evolution. It comes from a Hindu myth. However, it has 4 pillars that support the theory, and they stand on one grand mechanism. So that's why I've put it there. There is a story, by the way, related to a figure just like this, which is almost certainly not true. But it's such a good story that I'll tell it nevertheless. There is an Italian proverb, which is "Si non è vero è ben trovato," which means even if it's not true, it's still, it's a good story. So the story is about Bertrand Russell, the famous mathematician and philosopher, who gave once a talk, and he had a figure just like this. And some woman in the audience asked him, "On what does that giant turtle stand on?" And he said, "On yet another giant turtle." And she said, "On what does that turtle stand on?" He said, "Another giant turtle." But she insisted, "On what does that turtle stand on?" He said, "Lady, I'm afraid from there is turtles all the way down." Now, it almost certainly did not happen, but it's a good story. Okay, what are these pillars? Evolution, gradualism, common descent, and speciation. So first there is the concept of evolution itself, which means species are not immutable. The species we see today are not the species that always existed. In fact, most of the species on Earth have become extinct. Today, we just see what evolved from the species that once existed. So that's the first concept. The second is that of gradualism, and that Darwin borrowed from his geologist friends. In particular, Charles Lyell, the greatest geologist of the time, was Darwin's personal friend. And the idea was that just in the same way that the Earth is being changed continuously, but very, very slowly, that's how changes in evolution occur. Namely, you're not going to sit there and see one species turning into another. It takes tens and hundreds of thousands of generations for that to happen. The third pillar was that of common descent. Namely, Darwin says, all this enormous diversity of life that we see today, they all came from one, actually, form of life. And this is a very powerful concept because, people do, I have my friend Jack Shostak, who does origin of life experiments at Harvard. I mean, that's the idea. They think that life started once from some chemical processes and so on. So there was a first life form. And finally, there is speciation, which is, well, if all started from one, how come we have so many today? And to that, Darwin's answer is speciation, namely branching. Namely, things split. One species splits into two and the other splits and so on. And he drew this in his notebook to actually exemplify how these branches split. And since at every such node you double the number of species, then, very quickly you get to huge numbers. By the way, I like this page enormously, and I noticed that it is also, I think, on the back of this gentleman here, on his t-shirt, on the back of your t-shirt you have that drawing, yes. But you don't have the most important part of that drawing. I mean, I was sitting behind him, so I saw that he has this drawing. The most important part of this page is that Darwin wrote here at the top, I think. You see, so he was very humble at that point in his life. Okay, now as I said, these 4 pillars were supported by one grand mechanism, and that mechanism was natural selection. Daniel Dennett, who I'm sure many people here know in his books and so on, he's a philosopher at Tufts. He wrote once that he thought the natural selection may have been the greatest single idea that anybody has had. Now, I'm not sure about that, but certainly it was an incredible idea. And what's the idea? Like all great ideas, it is actually simple once it's pointed out to you. And the idea is, suppose you have a certain species, and suppose that certain members of this species have a characteristic that gives them a certain advantage in terms of both coping with environments, with other species and so on, and in terms of producing offspring, that they can produce more offspring. If that's the situation, Darwin says, then over many, many generations, the entire population is going to shift towards that characteristic. That's the thing, right? I mean, if those survive more and have more offspring, then after many generations, you'll have everybody having that. That's the idea. How do we see natural selection? Here is one very nice example. There is this light-colored peppered moth that was in England in the 19th century. And originally, it was so well camouflaged that, look, it's here, but you can hardly see it. But then, there was the Industrial Revolution in 1848, and they started pouring enormous amount of soot into the atmosphere, and the trees were blackened. At that point, this light-colored peppered moth was sticking out like a sore thumb, and it became the target of massive predation, and it almost became totally extinct. At the same time, the melanic, dark version of this moth started thriving, actually, because it was very well camouflaged. Now, luckily, even in 19th century England, they actually adopted somewhat greener practices, and as a result of this, at the end, the light-colored peppered moth was actually saved from complete extinction, and it still exists. This here on the right just shows a variety of rat snakes that, through natural selection, evolved to colors that match their environment, and so on. Now, where is the place where we see natural selection the most today? It's unfortunately in a not pleasant place, and that's it with bacteria that are resistant to antibiotics. I'm sure you know that, in the US, about 14,000 people die every year. Sorry, there is too much noise there. Can you perhaps close that door? I'm not sure what's happening there, but it's...
The party started early out there.
Can you close the door? What's the problem?
This door won't close. It's a device on the wall.
Okay. But you can hear me, right? Yeah. Okay. Where was I? Yes, 14,000 people die because of these bacteria that are resistant to all antibiotics. I mean, there's MRSA, but there are others. And we are a little bit to blame for it, but there are some industries that are more to blame, unfortunately. We are a bit to blame because, you know, we're sick, the doctor subscribes antibiotics for 10 days, we take it for 3 days, feel better, and stop. This is not good. This really develops bacteria that are resistant to antibiotics. But of course, the main problem is not that. The main problem is the enormous amounts of antibiotics that they feed cattle and poultry and so on for those industries, because it promotes growth, and you know they grow them in such condensed situations and so on. But luckily, about a year ago, finally there are some guidelines. They are still voluntary, but to actually have some control over the amount of antibiotics that one can prescribe and so on. So anyhow, the reason we see this in bacteria, of course, is because the populations are humongous and they multiply very, very fast. So the entire evolution process is compressed, and we see. Now, as you can tell from everything I've told you, Darwin wrote this fantastic theory that explains just about everything about life on Earth. So where is his blunder? I'm talking about blunders. The blunder had to do with heredity. Now, Darwin didn't know any genetics, and we cannot blame him for that, because nobody knew genetics at the time. So he adopted the theory of heredity that was prevalent at the time. That is okay. That's not a blunder. He could have done nothing better. That's what was available. The theory was that of blending heredity, which meant the idea was that the characteristics of the mother and the father get mixed in the offspring just the same way that you would mix paints. Okay? Now, like I said, Darwin adopting that, you cannot consider that a blunder, because that's what was known. His blunder was in not understanding, at least at first, that if that truly was the correct theory of heredity, natural selection could never have worked at all. And let me explain that. You see, let's suppose you have a population of about 1 billion butterflies. And they're all white, and there is one black. And let's suppose that it is black that gives an advantage in terms of you know, coping with the environment and blah, blah, blah. According to Darwin's theory of evolution by natural selection, the entire population of butterflies should have turned black after many, many generations. Now, what would have happened under blending heredity? The black butterfly would mate with a white butterfly. They would produce a gray butterfly. You mix them like paints, yes? That's it! Black has disappeared. Not only would not the population turn black, you will never see black again. That gray butterfly will mate with another white butterfly. Will get an even paler shade of gray of that butterfly. You will get not just 50 shades of gray, you would get 1 billion shades of gray from all these butterflies. But you will never see black again. It would not work. So, you know, it is really simple, and it is actually amazing that Darwin originally didn't see this. So this was pointed out by an engineer, Fleming Jenkins, in a review on the origin of species that he wrote. And, you know, it's really simple. Yes, you drink gin and tonic. If somebody keeps pouring tonic in, at the end you don't feel the gin, right? I mean, so that's how it is. Now, once it was pointed out, Darwin became worried about this. This just demonstrates here the difference between blending heredity and Mendelian heredity, which is Gregor Mendel's theory of heredity, which is a correct theory. You see, what Mendel taught us, that genetics works not like mixing paints, it's more like shuffling cards. You see, if you have an ace, and having an ace is good, no matter how much you shuffle, you still have the ace. That's what genes do. They are there forever. So basically, you see, in blending heredity, you have these two capital A's which give black, lowercase a give white. You get one from the father, one from the mother. they mix, they form gray. But not only that, the capital A, lowercase a in blending heredity cease to exist. They mix together to form something A1 and so on. That's it. Black disappear. In Mendelian heredity, you still get gray in the intermediate step, but the capital A and the lowercase continue to exist. And then depending on how they mix, two A's would give black, A with small a would give gray, the other one would give white. And if black is really very advantageous, then eventually the whole thing will turn black. Now, even though Darwin made this serious blunder, he actually was not happy with blending heredity long before actually Jenkins even wrote his thing. As early as 1857, this was before he published On the Origin of Species. He once wrote that he believes that it will turn out that propagation by true fertilization will turn out some sort of mixing, like cards, and not fusion, like paint. Okay? And then in 1866, he wrote to Wallace in a letter something that, you think about this today and you say, how didn't everybody who was talking blending heredity think about that? And that was, look, every female in the world produces a distinct male and a distinct female, and not some intermediate hermaphrodite. So it cannot be that there is this mixing like paints. So he understood that there was a problem with it, he just didn't know how to correct it. You see, Darwin's problem was that he was extremely weak in mathematics. So doing all these probabilistic calculations of how you mix and so on, this was beyond him. So that he couldn't do. Now, there have been no fewer than 4 books that claimed that when Darwin wrote this in 1866, it was not because he thought about it himself, but it was because he actually read Mendel's paper, which was published in 1865. I want to remind you, Mendel did these experiments with peas, green peas, yellow peas. He mixed them together and he got a ratio of 3:1, yellow to green, blah, blah, and so to write that thing. Now, I became a little bit obsessed with this in trying to figure out whether it's true that Darwin read Mendel's paper or not. And luckily for me, there was a guy, Andrew Sclater, from the Darwin Project, who did some excellent work before me on this, so I was able to build up on his work as well. So, okay, so let me then tell you what the story is. So first of all, Darwin did not have Mendel's paper in his possession. We know everything that Darwin had. We can see it all. He did not have it. That's not surprising. I mean, Mendel's paper was published in this journal of the Brune Academy of Science, which Darwin was not subscribed to. It was a relatively obscure journal. So that is okay. Now, those books, however, will tell you that Darwin had in his possession 2 books that mentioned Mendel's experiment. And that's actually true. He did have 2 books that mentioned Mendel's experiment. Now, one book mentioned it so briefly that there was no way to even understand exactly what Mendel did or to know anything from it. The second book is this book, which I also held in my hand because I asked it to be brought to me. You see, Darwin wrote his name here. It was the paper by this guy, Wilhelm Olbers Vöcke, and in it, there was a description of Mendel's experiment. So I asked for the book, and that's the book. I asked for it, they took a picture for me of this book. Do you know where Mendel's experiment is mentioned? Exactly here, in these uncut pages. You see, you may remember that in old books you had to cut the top. Okay, Darwin never read this book. It was in his possession, but he never cut any of the pages. Now, I will tell you that I actually read what's written in these pages, and had Darwin even read what's written there, he would not have been much illuminated, because Vöcke himself did not understand anything on the meaning of Mendel's experiment. So Darwin did not know about Mendel. Mendel, by the way, did know about Darwin, He had a copy, a German copy of Origin of Species. He actually wrote many notes in the margins. He underlined some lines. He actually used some of the text that he almost repeated it almost verbatim from Darwin and so on. Okay, I now go to the second person, which is Linus Pauling. Linus Pauling was born not too far from here. In early life, he lived in Portland, and then, of course, worked at Caltech. So he was kind of on both sides of here, I guess. Here is Pauling at a relatively younger age, pointing to this model of his for proteins, alpha helix. And here is Pauling when he was much older, but the model stayed the same because it was the correct model. So what was this model that Linus Pauling proposed for proteins? So in 1948, Pauling was in Oxford, England. He was on sabbatical there, and he was trying to determine the structure of some proteins. And he convinced himself that this carbon and nitrogen and the 4 atoms that connect to them have all to be in one plane. And then he wanted to see how he can fold these things so that it would still create a model for the molecule while keeping those atoms in one plane. Now, I need to tell you something about how Pauling was working. At the time that Pauling was trying to determine the structure of these proteins, they already developed quite well this method of X-ray diffraction, which was developed by the two Braggs, the father and son, Bragg. Basically, the idea was that you shine X-rays on the molecule, and from the way that they are scattered, you can actually try to determine the structure of the molecule. Pauling was working exactly the opposite. He first was trying to determine the structure of the molecules from chemistry ideas, you know, like the length of the bonds, the angles between the bonds, and so on. And once he constructed the model, then he used X-ray diffraction to try to confirm his model. So he came to the problem always from the other side. So in this case, after doing all this folding and things, he came up with this model, which he called the alpha helix. As you can see, it's a rather complex but beautiful model in which he thought he had everything under control. There was only one small thing. In his model, the distance between these two rounds, these two curves, was 5.4 angstrom. And the X-ray diffraction image has shown some signature as at 5.1 angstrom instead of 5.4. Now, you know, you can say, 5.4, 5.1. Close enough for government work. But he was unhappy. He was so unhappy that he didn't publish his model for 13 years. In those 13 years, he did everything possible to test his model. He asked Branson and somebody else to first see if there are any other mathematical solutions to this problem, and they didn't find. Well, there was one other solution called the gamma helix, but that could not fit everything in it. He asked Robert Corey, who was his assistant, to do X-ray diffraction of just small pieces of the molecule. And, you know, after he did all of these and all these tests and so on, he convinced himself that this has to be the correct model, and he published it. It turned out it was the correct model. The 5.1 angstrom turned out to be an artifact of the fact that there are two coils, one inside the other, and they produce these signatures. So he was very happy, and he had this model, and everything was great. Then he turned his attention to DNA. DNA is arguably the most important molecule there is. And very early on, in 1948, he wrote something that was remarkable in you know, its foresight. And that was, you see, he said something like this. I'll put this down for a minute and talk loud so that you can
here. Whatever molecule it is that is supposed to be responsible for replication, he said it's easiest to replicate if the model is composed of two parts that exactly complement each other. Because if they exactly complement each other, then it is enough for me to know half the molecule and the other half is determined automatically if it exactly complements it. So that's what he wrote there. If the structure that serves as the template is such, then it has two parts, then it is easy for it to duplicate itself. That was one thing that he said in 48. The second thing that he knew is known as the Chargaff rules, after chemist Erwin Chargaff. And you see, DNA, it was known at the time that DNA is composed of three parts. It's composed of sugars, phosphates, and four bases. The four bases are called for short A, T, C, and G. Two of them are single-ringed, two are double-ringed. What Erwin Chargaff discovered was that in any piece of DNA that he could take, the number of A's was equal to the number of T's, the number of C's was equal to the number of G's. And Pauling knew that as well. Okay? So then he worked and worked, and he came up with a model. What was his model like? It was horrible. It had three strands, three helical strands. Three. If you have three, how can you do complementarity? Why would you get A equals T, C equals G from three strands? Not only that, I mean, the model was really bizarre. It had the phosphates all in the middle with the bases outwards. But the phosphates are all negatively charged. And if you compress all the negatively charges together, they repel each other and they break the molecule apart, literally. It explodes like this. Okay? So, there was the greatest chemist in the world. I mean, you know, Pauling is one of those few people who got 2 Nobel Prizes. And he is the only person ever who have gotten 2 Nobel Prizes without sharing them with anybody. He got twice the Nobel Prize by himself. One for peace, but one for chemistry. But without sharing, neither of them. Okay, so here was the greatest chemist of the world. He came up with a model that at the wrong number of strands, was built inside out, and didn't obey the basic rules of chemistry, basically. Because you see, DNA is called, it's a nucleic acid, right? I don't know how many of you remember your high school chemistry, but an acid is something that when you put it in water, it releases hydrogen. Now, Pauling, he knew that if he puts the phosphate in the middle, they repel each other. So he wanted to have hydrogen bonds to connect it, to hold it together. But if the hydrogen connected together, then how could it release the hydrogen? You know, then the molecule would just fall apart. So this was really bizarre. Now, one of the things I've done when I wrote Brilliant Blunders was to try to think, to get myself into the heads of these people, to think why they made the mistakes they made. Now, this is hard to do. Yes, I mean, well, number one, I'm not a psychologist. Number two, even if I were, they're all dead. So I cannot talk to them. I did talk, in the case of Pauling, to everybody who is still alive and worked with him. His postdocs, grad students, you know, and so on. And there are at least 3, there are more, but at least 3 questions that you can ask yourself. First of all, do you know how long it took Pauling from when he started working on DNA until he published his model? Remember that it took him 13 years to publish his alpha helix model for proteins. Do you know how long it took him to publish his model for DNA? 1 month. So the question is, why the rush? Then, What about the Chargaff rules? You know, A equals D, C equals G. How does that fit into all that thing? So he forgot about this. Why did he forget? And then, what about the rules of chemistry? The thing just wouldn't hold together. What's going on here? So, I deal with it at great length in the book, but let me just give you a feel for what the answers could be. Why the rush? Well, you know, we're all human. Pauling was very competitive. He didn't know about Watson and Crick. He barely knew about their existence. But he did know that both the group in London of Maurice Wilkins and the group in Cambridge with Bragg had better X-ray diffraction images of DNA than he had. And he was afraid that they were published before him. What about the forgetfulness? He was even more human. Pauling just couldn't stand Erwin Chargaff. He was once on a boat with him on a trip from the US to England, and Pauling was a kind of laid-back individual. Chargaff was a very intense individual, and he kept nagging Pauling on the deck when he ran into him. And I think Pauling just basically took out of his head anything that Chargaff ever said. What about rules of basic chemistry? Pauling did not forget the rules of basic chemistry. He wrote the book on that, for heaven's sake. You know, literally wrote the book. Basically, here he more or less fell victim to his own previous success. Namely, you see, what the story with the alpha helix told him was that his original hunch model was correct. And all those 13 years and its checks and rechecks and so on only at the end showed that at the end he was correct. So he thought that that was true here too. He knew that there was a problem with the phosphates and so on, but he thought that will turn out to be a detail like the 5.1, 5.4 angstrom that would work itself out somehow. So he basically took a bet and he lost. Now, of course, the correct model was developed by Watson and Crick. The DNA has two strands. The bases are inside. A connects with D, C connects with G, which, number one, automatically obeys the Chargaff rules. Number two, it exactly obeys the complementarity that Pauling was talking about. You know half the molecule, you know the other half, and so on. Now, what did Watson and Crick do after they discovered their model? They were very young. You know, Watson was in his 20s, Crick in his 30s. They did what every two young people would do. They went to the pub. And this is the Eagle Pub in Cambridge, which is a wonderful place. And this is exactly the place where Francis Crick stood up in the middle of lunch and said, "We discovered the secret of life." And they have a plaque there now to commemorate this. I showed you Pauling when he was younger and when he was older. I showed you now Watson and Crick when they were younger, so I need to show you them also when they're older. Since then, of course, Francis Crick unfortunately has passed, but Jim Watson is still alive. I talked to him several times while writing the book and met with him once. So, yep, so that's their story. I put this picture here. It's a picture of a meeting on proteins that Pauling organized. And I put it here because of several, this is a remarkable picture for at least three interesting things. One is the large number of Nobel laureates in this picture. So here is Pauling himself, who's a Nobel laureate. Here is Maurice Wilkins, who's a Nobel laureate. John Kendrew is a Nobel laureate. Max Perutz, a Nobel laureate. Jim Watson, Nobel laureate. Francis Crick, Nobel laureate. Lawrence Bragg, Nobel laureate. Many Nobel laureates in this small group of people. Second, only one woman, Beatrice Magdoff of the Brooklyn Polytechnic. You go today to a meeting on proteins, easily half are women. So some things have changed. And finally, you see, this is a science meeting.
It's not a business meeting. This is a science meeting. Now look at these guys. Look, I'm not wearing a tie now. They're all wearing ties, for heaven's sake. I go to a science meeting today, nobody wears a tie. Unless it's a meeting of medical doctors or business people. But scientists, they never wear ties. Here, everybody wears a tie. So some things have changed. Okay, the last person is Albert Einstein. This is the picture of him I like best. When my hair is a bit longer, it looks just like that. You know, I like to say that there are other similarities too, like, you know, Newton is dead, Einstein is dead, and I also don't feel so well. Now, Einstein's greatest achievement is, of course, its theory of general relativity. Now, some of you may be a bit rusty on your general relativity, so I'll explain to you with one slide what this is all about. No, wait. I don't mean that you should read these tensors there. That's not the problem. But I'll explain to you the meaning of this equation in very simple terms, and you will see that you understand what I'm saying. Forget for a second about this term here. This thing here expresses all the mass and energy of the universe. Okay? That's what this is. This is the strength of gravity. This thing here is the geometry of space-time. The geometry. So what Einstein tells us is that the mass and energy content of the universe determines the geometry of space, and that's what gravity is all about. The curvature of space. In other words, you know, like if I stand on a trampoline, I cause it to sag. If you will now throw some small balls onto this trampoline, they will find the shortest path in this curved space. That's what masses do. Gravity is not some mysterious force that acts across distances. It's just an expression of the warping of space. The sun warps space in its vicinity, and the planets find the shortest paths in this warped space. That's what general relativity is all about. And that's it. You don't need to know anything more than this. Now, once Einstein had this beautiful theory, which, by the way, we're celebrating 100 years to his paper on this, 1915. So, celebrating 100 years. We're also celebrating in 1915, 25 years to the Hubble Space Telescope, since launch. So, indeed, once he had this theory, he tried to apply it to the universe as a whole. But he immediately realized that there was a problem. You see, he thought that the universe was static. He didn't know about galaxies, by the way, at the time. He only knew about stars. But he thought that stars are basically static. He thought that that's the most beautiful solution, that everything just stands in place. But how can everything stand in place? If every mass attracts every other mass, how can things stay static? This would just collapse on itself, right? So he realized this. So he didn't know what to do. So he added this term here. And this is called the cosmological constant, which basically at every point he added a repulsive force that exactly balanced the attractive force of gravity. So at every point, if it felt some attraction towards here, he added a repulsive force that exactly balanced this. Now, it turns out it was not a great idea, anyhow, because while he could construct an equilibrium this way, it was an unstable equilibrium. It's like if I balance this on my finger. I can do it, but the slightest deviation, would cause it to fall. So, but he was happy with it because he had constructed an equilibrium. Okay. Then these two gentlemen came. This is the cosmologist and priest, Georges Lemaitre. And this is Edwin Hubble, after whom our telescope were named. And in between them, they discovered that you would often hear that Edwin Hubble discovered this, but Georges Lemaitre actually discovered something along those lines before Hubble. They discovered that our universe is not static. Our universe is expanding. When Einstein heard that our universe is expanding, he said, wait a second. If the universe is expanding, I don't need to balance everything at every point. Because all that gravity will do now, it would just slow down the expansion. See, like, you know, I'm taking my keys, throwing them up. What the gravity of the Earth does, it slows down the expansion of these keys, right? Going up, right? The keys are not in equilibrium. Just the gravity slows them down. So Einstein said, if the universe is expanding, I'm sorry I've even put that term in, because all that gravity will do is slow down the expansion of the universe. So he regretted having put that term in, and he took it out of his equations. Okay? Now there is a whole story on whether or not he called this the biggest blunder he ever made to put that term in. You can read about this in the book, but I would not tell you now. But that's not the point. He did regret having put that term in, and he took it out of the equation. Then, in 1998, two groups of astronomers working independently discovered that not only is the expansion of our universe, is our universe expanding, but the expansion is not slowing down. It's speeding up. It's accelerating. Now, this is pretty amazing. You know, I mean, if I throw my keys up, and not only they don't slow down, they start accelerating towards the ceiling, you think that's magic, right? I mean, well, there is something pushing on that, you know, that is causing the universe to accelerate. Those two groups, by the way, the leaders of the groups got since the Nobel Prize for discovering this accelerating universe. Okay? So, do you know what, as far as we can tell, is pushing the universe to accelerate? It's that term that Einstein took out from his equation. So if he did any blunder at all, it was not putting that term in. It was taking it out. Had he left it in, he might have predicted that the universe should be accelerating. So that's the story. You see, some people just so smart, like Einstein, that even when they think they made a blunder, that turns out to be a huge insight. Okay, I now want to come back to the main question with which I started, which was how science progresses. So, very often in stories in media, even in textbooks, even the way we're taught, progress in science is described as some sort of a success story. It is this direct march from A to B. That's not like that at all. Science progresses more like this. So it's a zigzag path with lots of false starts, lots of blind alleys, lots of points where you need to start to the beginning and start again. That's how science really progresses. And it's not just science, by the way. It's any creative process that works like this. But there is even something deeper here that I want to convey, and that's another main reason why I wrote the book, and that's the following. You see, we have grown to despise mistakes. Children are taught now that they cannot make mistakes, basically. when they make mistakes, they are basically punished for it. Now, I want to make it very clear. I don't advocate making mistakes if those mistakes are made because you are sloppy, not thoughtful enough, or inexperienced. Those are inexcusable because you shouldn't be sloppy and you should always think hard before you do something. And if you're inexperienced, you should ask for guidance. What I do advocate very strongly are these things which you see I entitled my book, Brilliant Blunders. These are the blunders that you may make because you are trying to think outside the box. You see, we want to encourage everybody to think outside the box, right? Well, guess what? When you think outside the box, you sometimes make blunders. That's how it works. Now, you live here very near a place which actually has adopted that as their philosophy, which is all the startup companies, right? Startup companies, if you look at them 4 years down the road, more than 50% of them no longer exist, right? But some of them lead to breakthroughs. So the idea is you should think you should make the processes such and the education system such that it allows for unconventional or outside the mainstream thinking. And I mean by that in terms of grades you give. People ask me all the time, how do you do this? Look, I'm not a professional educator, so I don't claim that I know the precise answer of how to implement what I'm just suggesting. But I'll give you one very simple example. If you make all your questions in any test multiple choice, that's definitely not the way to encourage this. Because in multiple choice, there is one answer which is correct, and everything else you mark is incorrect, and you don't know if the kid was trying to think really in a very smart way, and that's why she chose that particular answer. So make some of the questions not multiple choice, for example. I'll give you an example from funding, in grants and so on. For about 10 years, we adopted with Hubble, so every year, about 1,000 people propose to observe with the Hubble Space Telescope. We have a very elaborate process which decides which proposals are being approved. And roughly it is 1 out of 7, but sometimes it is even as low as 1 out of 19. We have an enormous oversubscription. Nevertheless, for about 10 years, we allocated about 10% of the telescope's time to proposals deemed risky, which meant proposals that were well thought of, but where it was not entirely clear if they actually can achieve the goal objectives that they have. But that if they can, this could be a very interesting result. Okay? So that's the way how to implement it within, let's say, funding agencies and so on, to allow for this type of thing. The former head of IBM actually adopted this as a philosophy of the company. Used to say, we shouldn't punish anybody who made a mistake while thinking in the benefit of the company, and so on. So that is my key message here. So basically, I'll finish here by saying that scientific blunders, and in particular these things which I call brilliant blunders, can, and very often are, the portals to discovery. Thank you very much. Happy to answer a few questions if there are.
Yeah, folks, if you have your questions, the microphone is over here. The line starts behind Bill. I don't know if he's first or not.
No, I'm not. So I'm just here to locate the microphone for anybody who wants to use it.
Yes.
I'd like to ask a question about Linus Pauling.
Yes.
He and as he got older in his life, he got really gung-ho about vitamin C. And as I look back, and you mentioned his rush and his forgetfulness, I kind of tie it to, do you think perhaps he had a coming Alzheimer's going on? I'm just curious.
No, well, first of all, I don't know if he had a coming Alzheimer's because I don't know his medical condition. But I actually do have a theory about what he did concerning vitamin C. And actually, that is not something that just Pauling did. We have examples of a number of great scientists who, at some point later in life, did something that turned out not to be particularly smart. And the way I think about this is something like this. But again, it's a theory. I cannot say that I know this for a fact. If you are somebody like Pauling, namely a gigantic scientist who has had enormous achievements in a number of ways, then sometimes those people don't find it satisfying to then engage in relatively mundane research and continue to do things that, produce at best some small incremental change, or advance and so on. They don't find that satisfying. So they try to hop into something new about which they know relatively little, and they try almost to by force to make a big step in that direction as well. So that's how I regard Pauling's vitamin C efforts.
Thank you very much for your talk. I really appreciate it, first of all. I run into many people in my life who think that evolution is not a real fact, and I try to help them out. You talked about speciation. I think was a term you used in terms of gender. When someone is born, they're a male or they're a female, and they're demonstrably so. It seems like I had read somewhere that something like the same number of people with red hair are born, and their genitals don't lean towards one gender necessarily. And I wondered if you could talk about that, whether or not that's a true fact, and how that impacts the truth of Darwin's theory.
Yeah, no, I did not relate that to speciation. I just related that to the fact that there are genes. Okay. And so it is determined, whether you have XX chromosomes or XY and so on, that determines your gender, basically. While if you actually really had mixed the characteristics of the mother and the father, like you would mix paint, then there wouldn't be this situation where you would get a specific male or female. Now, about red hair, I don't know specifically about red hair. I'm not even sure what you say.
I was using that example in terms of the number of people who are born and have genitalia that doesn't fall strictly into the male category or strictly into the female category.
But I think those are probably relatively rare cases. Right?
Yeah, they're very rare.
Right,
I only bring that up because this is something that gets thrown back in my face by people who say that evolution is not correct.
Yeah. No, right.
I wanted to know, in dealing with Einstein's blunder with the cosmological constant, I had read that maybe one of the reasons he labeled it the cosmological constant is that he was afraid to admit that there could have been a beginning to the universe and expansion, and that's why he put that in there.
No, that's not true, because actually the term cosmological constant was not even coined by Einstein.
But the
it was actually coined later, that term. So no, I don't think that's actually true. In fact, Georges Lemaitre, that I mentioned, was this Belgian priest who is the first person to have suggested that there was a Big Bang. He once jokingly said that he, as a priest, prefers that the universe had the beginning at one point, but he was really joking.
Okay, thank you.
I believe the group here and I would appreciate your comments on the James Webb Telescope.
Sure, yeah. So the James Webb Space Telescope is the scientific successor of Hubble, but it's not the successor in terms of its functionality. Hubble is a telescope that observes mostly invisible light. That's the kind of light that you see. A little bit in ultraviolet and a little bit in infrared. The James Webb is an exclusively infrared telescope. It observes in infrared. And the reason for that is our universe is expanding. As our universe is expanding, light is being stretched. And so visible light becomes infrared light. So if you want to see deeper and deeper into the universe, you want to look in the infrared. So that's why James Webb is in the infrared. In addition, because it's infrared, infrared is also heat radiation. The telescope needs to be very far from any sources of heat. So Hubble is in a low Earth orbit. It's just 350 miles up. James Webb could not be there because there's too much heat from the Earth. So James Webb is going to be at Lagrangian point 2, which is 1,000,000 miles from Earth. It is not serviceable, and it has this enormous sun shield that also shields it from any heat and from radiation from the sun. It's the size of a tennis court, the sun shield. The telescope is also much larger. Hubble is 2.4 meters in diameter, the mirror. James Webb is 6.5 meters. So it's a very different telescope with very different capabilities. It's currently on track to launch in October 2018. So that's when we hope it will launch.
Well, first of all, thank you again for coming to share your insights on that.
And by the way, my institute is going to run the James Webb Space Telescope as well. So that's why I know so much about it. Yes.
If we look back in the 50s to the 70s, a lot of the major corporations, IBM, AT&T, Xerox, HP, had large research labs who were trying to stretch themselves. In fact, I know with the HP side, they said if they weren't failing, if they were succeeding more than a certain percent, that was a failure.
Right.
They weren't pushing hard enough. I don't see that nowadays. I do see the Silicon Valley startup kind of innovation going on there, but have we lost something with the corporations in terms of their research?
Well, let me just say, first of all, that I don't know enough about this to give you a really informed answer. I know that IBM still has a fairly large research component to it.
A lot of those are focused to specific desired outcomes.
Yeah, but and certainly there are large companies. You know, Google is a large company, and they have, of course, a very large research component to them, and so on. But it is very possible, like I'm saying this without knowledge of the actual numbers, it's very possible that much of the research effort has been shifted more towards these startups or, you know, companies like Google, you know, and so on, and maybe less so into the companies that build hardware necessarily and so on. But certainly, look, I mean, all the companies that, for example, manufacture medications, they have large research components to them, you know, and so on. Now, of course, their research is, on one hand, well motivated. On the other, of course, they want to make profit too. So, you know, there is a balance, I guess, between those two.
Try to be close to the microphone, to about 3 inches.
Question, who is the real father of the DNA molecule? Is it Linus Pauling, or is it the two men who came after him?
So it's really Watson and Crick. But the reason that I still think that Pauling's was a brilliant blunder, even though it looks like a horrible blunder, is that actually, believe it or not, Watson and Crick actually adopted precisely Pauling's methods of thinking about the molecule, and that's what led them to the actual solution. Pauling made a mistake along the line. Basically, he had the wrong density, and this is why he introduced the third strand and so on. But they really emulated Pauling in their research to discover the structure of DNA. I should mention, just so that it will be clear, that a person who played a crucial role in the discovery, even though she didn't discover the structure itself, was Rosalind Franklin, whose incredibly detailed X-ray diffraction images of DNA allowed Watson actually to conclude that that was the correct model. So unfortunately, she died very young of cancer. She died before the Nobel Prize for that discovery was given. I must say that had she been alive, probably the Nobel Committee would have had a serious problem on their hands, because traditionally the Nobel Prize is not given to more than 3 people. The 3 people to whom they gave it were Watson Crick and Maurice Wilkins. And Maurice Wilkins no doubt did a lot of important work in studying the structure of DNA, but Rosalind Franklin was essential in all of that. So I'm not sure what they would have done had actually all 4 of them been alive at the time they gave the Nobel Prize. Yeah, thank you. Any other questions? If not, then, oh yes?
This is sort of personal,
Yeah.
but I still don't like the base validity of the Big Bang. Why did it happen? Why then? How? I don't like it. I'm still looking for alternative theories. Anybody out there is crazy.
No, the Big Bang, the Big Bang is great. I'll tell you. It's great. I mean, I can talk about this for a week, but it's a wonderful model, and it really works. Believe me. Stay assured that the Big Bang is fantastic.
Okay, here we go. Thank you again very much, Dr. Lieber. And Phil, about the Big Bang, Phil, all I can say is there's thinking outside the box, and there's putting your box on another planet, where there's nothing else but the box. And not sure that's very productive. All right, since it is about time, we have cake, we have goodies, we have things to celebrate, of course, the birthday of Charles Darwin. That means, of course, before we can do any of that, we have to sing happy birthday. Who would like to start? Okay. Well, that requires, yeah, actually, we're, no, not happening, okay. Well, it's in lieu of my voice, but I'll cue everybody. All right. Happy birthday to you. Happy birthday to you. Happy birthday, dear Charlie. Happy birthday to you. Happy birthday, Chuck. Folks, thanks very much for being here. Obviously, Dr. Levy is going to be here to answer any questions you might have that you're embarrassed about asking publicly. We have cookies, cakes. Good Lord, I can see the food from here. It's piled to the sky. Please take advantage. Please indulge. Have a great Darwin Day.